Hello class, this is the last slide that we discussed in last class. So in this figure we defined our feasible region by incorporating all the constraints. So this blue color is our feasible region. So if we enlarge this, so our optimal solution will be one of all the points in this feasible region. So our objective function is 10s plus 9d, 9 times d. So 10 times the number of standard bags plus 9 times the number of deluxe bags. So we can draw multiple lines through this figure. So on each line, so all the points will return the same objective function value. For example, on this line, all the points on this line will return the value of 1800. So our job is to find which point will return the highest value. Okay, this one, or maybe this one, or this one, or which one. So in this figure, we can see that there are some special points, 1, 2, 3, 4, 5. So they are called extreme points. So based on the theory, the optimal solution has to come from one of the extreme points. So extreme points are found where constraints intersect on the boundary of the feasible regions. So two constraints may define an extreme point. Okay. So if we calculate the objective function values for all the extreme points, so here are all the extreme points and the corresponding profit or objective function values. And for the third one, so in the textbook the value is wrong, so the profit should be 7668. So the third point, or the third extreme point would be our optimal solution. So optimal solution would be to produce 540 standard bags and 255 deluxe bags. But in real application, how do we solve this model? We cannot just draw a diagram or draw a figure like this and try to find out, okay, which is this one or that one or that one. So we have to have an algorithm to help us to search for the optimal solution. Okay, so that method is called simplex algorithm. So this algorithm is developed by Professor George Danzig. So Professor George Danzig was a professor from Stanford. He already passed away. So he was the one who developed this very, very, very popular algorithm for solving linear programming model. So basically, the logic of this algorithm is to model the feasible region as a polytope. So we know in the polytope we have edges and we have a lot of extreme points. So we can, in this algorithm, we consider that first of all, the extreme points are our candidates for the optimal solutions. So the algorithm will search each of the, not all the extreme points. So the algorithm has to start from 1 and then record the objective function value, and then along different edges that are connected with that extreme point, and they search for the next extreme point and see if the next extreme point has a better solution or not. Then by doing this kind of search, so the simplex algorithm will return us with the optimal solution. So Excel has this simplex algorithm, so you can use Excel solver to solve this linear regression model. So let's open okay. So let's open the data file. So we have the model implemented in this Excel file. We have the constraints, or we have the parameters, we have the constraints, and we have two distinct variables, and I think we modeled, we have this file from the last class. So what we need to do is to go to the data. So here is a function, the Excel solver. So in this interface, we need to define a few things. The first one is to define our objective function or objective. So our objective function is in cell B16, so that's the profit function. So that's our objective function. And also we need to select, are we going to maximize this value or minimize the value? So in this case, we want to maximize our profit. So let's select maximize. And the next one is to define the decision variables by changing variable cells. So we need to tell Excel, okay, here are our decision variables. So in this case, our decision variables are number of standard bags, number of deluxe bags. And the next one we need to work on is the constraints. We have to make sure the hours, the hour use for each of the processes will be less than or equal to the available hours for each of the process. So those are the constraints. And here we are going to select simplex linear programming. So, and we click solve. Okay, keep solve a solution. Okay. So, then we have the optimal solutions. So optimal solution is to produce 540 standard bags and 255 deluxe bags.